All right, guys, so several questions. First question is, have all of you submitted my second exam? Okay, fine. And the second question is, there is still I think maybe one or two people, they were sick, they are taking slightly longer. If you still want to make corrections to the second exam, you still may, until I think Wednesday. Yes, I can hold on maximally until Wednesday, especially that I'm sure you are very interested in looking at the solutions to the exam, correct? To see whether you are right or wrong. And not just that, to really see things deeper. Maybe some of the questions will open your mind to think that you never considered before, correct? Yes, Chiara is excited. It's very good. So I think, when is the last day of class? It's today, correct? Officially.
Yes, today.
But that's only officially, right? The probability, once you start, it never ends.
Absolutely.
I would be, of course, happy to continue. I'm not sure you would be as happy as I. So I think we might hold a session on Wednesday optionally for those interested in the result of the second exam. Yes? Would you like that, guys? Just want to see as a vote how many of you would decide to join at a regular time on Wednesday to do a session where we discuss each and every question of the second exam and how I think to solve it. Yes, good, useful. So you will come. And maybe third or fourth item is today is the last day to submit teacher evaluations if you intend to do so. I would appreciate it, because I hate it when it's only partial. I think if you have only 10 people, I mean, I think, is it a good sample or not, right? It's not random, I'm sure. I appreciate it. It's completely anonymous, although I sometimes can figure out who wrote what, and I will hunt you if you write something. No, I'm joking. I'm not going to hunt you. I do enjoy, if I caused you suffering, I might enjoy it as well. You know, I mean, there was one person once who wrote, you should go over more problems and perhaps over a bridge. All right. So it was a funny one. I enjoyed it. You can try, see if you can offend me. Right? All right, guys, so let's go on with the lesson. Maybe we will even have a short lecture today, unless you really want to cover more material than I have planned. We actually made time. And I think, my God, I should have squeezed moment generating functions. So I'm not sure I'll do it today, as I didn't prepare the lecture. I can kind of informally talk about it, but maybe it will not be good. So here is what we have available for today. Joint distributions, where we have, of course, first independent random variables. And you know, guys, that x and y, two random variables, are independent if x in A and y in B is the same as the product px in A times py in B. Yes, and you understand why this is the case, correct? It's just directly from conditional probability that you have this result. This translates into a statement about cumulative distributions, which is this. So the cumulative distribution is just probability of the x separately and the probability of y separately. Actually, whenever two random variables are independent, any expression of probability about both of them is the product of one with the other. Okay, so this is an expression of some probability involving x and y, and those probabilities are not influencing one another in a sense, right? So that means this is what you should have. Good. And in terms of cumulative, cumulative mass function, it's just the probability at x times the probability at y. So as I mentioned, one direction is obvious. This probability that x is in A and y is in B is just the summation of all combinations of x and y that contribute to this event. So it's all x and y such that the first coordinate is in A and the second is in B, and we sum over all of them. That's all this summation means. There is just nothing beyond that. And if they are independent, you see, it means it's just the probability of x times the probability of y, and that means we see just a foiling of two parentheses. It's like an expanded form. You have one parenthesis summations of the x's and one parenthesis summations of the y's, and they were multiplied through. You can see that, yes? Or if you want to, I can show you some examples, some sort of pseudo example or example, which is good or not. What do you want to do, guys? Should I give you an example or whatever, right? I think you don't need it, right? Okay, I see. Yes, an example. I shouldn't have offered. All right, let's see. So suppose that what we have is just to make it simple. We have two events. We take a fair die, right? We take a fair die and we take a fair coin. And then we have x is going to be the expression of the fair die and y the expression on the coin. Yes. So then we might consider, for instance, A, the event die is even, and B, event coin is tails. Okay, event coin is tails. So so that if we prefer numerical values, we might imagine the coin is 0 if heads and 1 if tails. Good. We can just assign a code. So then what is the code space for the combined distribution x and y? So x and y is a collection of vectors x, y, such that x is a number 1 through 6 and y is either 0 or 1, where 1 being tails. Good. So what do we want? We want what is the probability that x is in A and y is in B? This is just the probability of the probability that x is equal to, so x in A it's even, so x is equal to 2 and y is equal to 1, right? Plus the probability that x is equal to 4 and y is equal to 1, correct? Plus the probability that x is equal to 6 and y is equal to 1. I think I haven't missed anything. Yes, those three possibilities. Good. So this expression I could have written, especially if you have lots of possibilities, I could have said, oh, this is over all x in A and over all y in B, right? So actually, to make it slightly shorter, here is how this summation works. I mean, it's easy calculation, right? I mean, it's not the point to calculate the probability. The illustration is essentially to understand this general statement about independence. So it's not really about the probability, but really about what is this summation supposed to tell us. Just a few people asked me for an example, so I'm going over it this way. Okay, so I'm trying to, again, guys, hopefully you see what my goal is. I'm just trying to explain to you what this notation, what this means, right? So that it's actually almost not worth writing. So it's x in here. So what is this? This now means x in A. So it is px1 in this case, right? Because only there's only one possibility for y. Actually, there is nothing more, but it could be that there are more possibilities for y. It could be for any x there is whatever y, right? So that could be in general written like this. Right, the summation, just of these two combined sigmas, is just all the combinations. So sum every x that belongs in A with every y in B and calculate the probability. Okay, that's true regardless, independent or not. The thing is if you have independence, then we can then write probability of 2, 1 as probability of 2 times probability 1, right? And the next one yeah, I know. I mean, it's so magical. You begin speaking in foreign tongues. You know, it's as if the devil is in you. Yes, Lauren, or who was that speaking there? So it's this thing, and in general, so what we have is that the probability of 2, 1 plus the probability of 4, 1 plus the probability of 6, 1 is probability of 2 times probability 1 plus probability of 4 times probability 1 plus probability of 6 times probability 1. Yes, so which you can, of course, look at it, you can factor it, right? You can factor the y values. You can factor the y values, so you can write as probability of 2 plus probability of 4 plus probability of 6 times the probability 1. You can factor it out. And if you had more versions of y, you could still factor all of the y's out. You would have parentheses all the x, parentheses all the y. Yes? And what would fail? You see, if you don't have this property, some of those probabilities might be 0, you understand? Or they would not equal to this factored form, so you cannot pull one sum from the other. I hope I am understandable. So this is what this is said. So, and of course, as I mentioned, is that independence in the continuous case means that the density function breaks apart like this. And the reason the density function breaks apart like this is very similar. I mean, what is the probability that x belongs to A and y belongs to B? In the continuous case, this is the integral, same thing, the integral over A, the integral over B, right, of f x y dy dx, which if this probability breaks apart, I can just, again, it's just like summation, just like before. If it breaks apart, I can write it as the expression for x. This is the probabilities of x multiplied by the probabilities for y. Yes. So if you should think very carefully and see that you understand that it must be this situation, right? And here is a simple example. If I have n plus m independent trials, and the probability of success is P if I let X be the success on the first 10 trials and Y the success in the last M trials, then of course they are independent. The trials are independent, so just it's an arbitrary breaking them into two groups. So that probability is N choose K. That's the probability that within the first N I have K successes, and this is the probability that within the first within the M I have, the last M I have J successes, and that's going to be, of course, probability X equal to K times probability Y equals J. And there is, of course, nothing special about just having two random variables. I can say that the N random variables are independent if they satisfy this relationship for any collection A1, A2, AN, right? So if X1 is in A1, X2 is in A2, and so on, then it's a product, yes? And then here is an example. So let's say you are going to try to calculate. Since we have a little bit time, I might wait a little. So each Calculus 1 student joins the video lecture independently with a beta distribution B31. If there are 12 students, the rest don't bother to show up at all. Compute A, the probability that 10 or more join within the first half of the lesson, and B, the students log on in alphabetic order. So let's calculate A. Do you understand the question, guys? So the distribution for each student is beta 31. You remember what it is, yes? I gave you an easy beta version, right? So go ahead, calculate. I'll wait a little. Rather, beta distribution does not go to infinity. I mean, right? And it doesn't even begin with 10. A beta distribution is always from 0 to 1. Right. How is it going, guys? You're close to the solution? Okay. Okay, well, the function just normalize the integral of p squared. And to normalize the integral of p squared to equal to 1, what do? You just first of all, you should know how to calculate beta for any pairs of integers, because we derived it. There is a way to do that, but from memory, it might not right away come. Right? So how do we solve this question? This just means p to the power of 2 times 1 minus p to the power of 0. Just subtract 1 from each of them. Yes. So it's really p squared that we're dealing with. And the coefficient, the beta coefficient is just a normalizing factor, because if I integrate p squared, I get p cubed divided by 3, correct? And then if I plug in, if I just integrate it from 0 to 1, I am supposed to get 1. But if I plug 1 into p cubed over 3, I get 1/3. So I need to multiply by 3. Right, so the function is just 3p cubed that I'm integrating. The beta function is actually just 3p squared, not 3p cubed. 3p squared. Good. So how do we do that? Well, here is the solution. Here is my solution for it. So first we have student 1, student 2, all the way to student 12. And those are just the different random variables. And each of those random variables are twins. They're identically distributed, and each of them will be 1 present, or 0 absent. Correct? So what was the question? So I said that 10 or more join within the first half of the lesson. Right. So what does it mean for student K to join within half of the lesson? It means that student K arrives from 0 to 1/2. Right. So the arrival time for the lesson is a beta distribution. So it's you have the probability of arrival, right? So that means that if I integrate it, probability of xk less than or equal to 1/2 is the integral from 0 to 1/2 of 3x squared. You understand where I got the 3x squared? Because I was told that the distribution of arrival for each of them independently is beta with parameters 3 and 1. So we have 3x squared from there.
So that's from the p to the power of a minus 1 times 1 minus p to the power of b minus 1.
That's correct. And then I just normalize it. I mean, I don't have to remember the beta coefficient, but I just know the integral from 0 to 1 has to be equal to 1. Right?
Right. So my question I get a little confused on is the constant in front of the x.
Yes, well, that's because what is the beta distribution? Don't think of everything. Beta distribution is just p to the a minus 1, 1 minus p to the b minus 1. Yes. So
right.
Essentially, it is like it's very similar to part of the binomial, right? Now
right.
there is a constant. Why is there a constant? Because the integral of this from 0 to 1 dp has to equal to 1. Yes, the integral of this has to equal to 1. So this constant has to be so just the constant. If I just have it as 1, this integral might not be 1. So if I just integrate c p squared dp, what do I get from 0 to 1? I get c multiplied by 1/3. Do you agree?
Yes.
is 1, so C has to be 3. So
Okay.
this coefficient, that's how I got this 3.
Okay.
Make sense?
Nothing to do with the like n choose k thing that shows up in the pattern.
Well, that's the general way to do that.
Right.
Just in general, it's not so easy to figure out look what I did here. I integrated it. If you could easily integrate the expression p to the alpha times 1 minus p to the beta all the time, then it will be easy to figure out C the way I just did. But if you have 1 minus p to some non-zero power, it can be difficult.
Right.
Yeah, so there is a combinatorial way of doing it in general. But you can recall it, and I always advise you guys to recall it and just see if you can do the combinatorial identity for it in general. But if you don't have time or you're just doing something on the spot, you can just integrate it in some special cases. Good, but do the combinatorial identity. That should work all the time. You don't need to integrate them. Okay. So what we get is that the probability is 1/8. It's of course very generous to assume it's not likely to be a correct distribution because of course, well, I mean, I'm assuming this means that arrival happens for each student within the time, right? Maybe I said beta because let's say if it happens to equal to 1, that means the person did not arrive. But I mean it's actually in real life obviously much more likely to be equal to 1 or more in that case, right? So it would not be beta distribution. Those are still fairly good students, much better than real ones, right? Because they do arrive, all the 12 students do arrive within the lesson, just not usually on time. So what you have is this is the integral to 1/2, and that gives you 1/8 as the probability that student number k comes within the first half hour or within the first half of a lesson. So now all we are dealing with is binomial. Do you agree? Because now we are saying let's estimate what's the probability that what do they say? That 10 or more, it's k equal to 10 all the way to 12, right? And it's a binomial, right? And if you calculate this binomial, what do you get? You get that this probability is extremely low. It's 4.8 divided by 10 to the 8, right? So it's very, very unlikely that 10 or more people will arrive within the first half an hour. Okay, and then what about B? B is asking for the probability that students log on in order, by alphabetic order. That means what? In terms of integral, that means first is x1, then x2, then x3, all the way to x12. Right, and that then becomes this integral, very kind of ugly integral from 0 to 1. That's for the for 1, from it can arrive at any moment. Second person arrives from x1 to 1, third from x2 to 1, because they're always later than the previous one, and so on and so forth. And this integral is not easy to calculate. Actually, thinking combinatorially does help in certain situations. I haven't explained it, but Poisson paradigm, for instance, recently I thought about it and I figured how the Poisson paradigm works. Where I read it, it was not explained. So, so what is the easier way to do that? How to solve this integral? Well, to realize that since they are identically distributed, there is no preference in the permutations where they arrive, right? So every permutation of x1 through x12 is equally likely, correct? They're identically distributed, so that means that there is no preference for person 1 to arrive before person 2. So any mixing of them, any reordering of them is equally likely, which makes this very ugly integral. You can make a computer do that if you want, but this very ugly integral has to be 1 over 12 factorial. Nice, right? It's enjoyable when you don't have to do any work. Poisson, again, Poisson is an approximation of binomial, either binomial or something similar to binomial, right? In other words, where you have success, failure, success, failure. Here you have ordering. I mean, if you have to then describe ordering as success or failure. You can try, of course, right? But then you have to describe it as success or failure. It's easiest, I think, to just in this particular case to do it in one, just observing that every permutation is equally likely. Right, so it's, you see this, just interpreting this integral, you know that the answer is 1 over 12 factorial. You can, by the way, experiment with a computer. If you don't believe me, select a smaller value. Let's say select only 3 students and see that it's going to be 1 over 3 factorial, right? And then you can be convinced it's correct. Well, here is another example. A man and a woman decide to meet at a certain location. If each of them independently arrives at a time uniformly distributed between 12 noon and 1 p.m., find the probability that the first to arrive has to wait longer than 10 minutes. Make sense? So each of them arrives to a location uniformly within the hour. And the question is, what's the probability that the first to arrive waits longer than 10 minutes? Think about it a little bit. All right, well, let's do it together, I suppose. So we can say X and Y be the times for the woman and for the man. So X is a woman, Y is a man. And what do we know? So we can do that, let's say, by the minutes. We said 10 minutes. So I say uniform distribution for both X and Y between 0 and 60. Good. So what does it mean for the man to arrive 10 minutes after the woman? It means that Y is bigger than X plus 10. Do you agree? X is the moment of arrival of the man and Y is more than X plus 10. And if the woman arrived later, right? The woman arriving later means it's a similar inequality, just swap X and Y. That means that man is arrived at Y and the woman arrives later than Y plus 10. And by symmetry, of course, it cannot happen that that you have both events. They are mutually exclusive. So it's the summation of those two events. And of course, by symmetry, we can say that this part and that part are the same. So what we have is 2 times the probability that Y plus 10 is less than X. So that means that it's twice the probability that the woman arrives 10 minutes after the man, or more, right? So what do we get? We have this integral. And what's the density function for this integral? They're independent, right? So f of xy is 1 over 60 squared. You agree? Why? Because for the man, it's 1 over 60. It's basically, its distribution is over 60 minutes. So it's like a box. The width is 60. The height has to be 1 over 62, have area equal to 1. And same for the woman. So by independence, it's f of x times f of y. So it's 1 over 60 squared. And the integral is from what to what? The integral is for x. X is, so the integral for the, let's see, what is it? So it's we just have to set up this boundary, right? So for this boundary, we can specify y, right? And then x has to be 10 later, right? So I think, what did I set it up? It should be, I think, I don't know, I mean, why is it 10 here? I think it should be, if I set it up with x on the outside, that means that well, I suppose yes, that's right. If x is on the outside, then the only way y had to wait 10 minutes is basically for any x, for any x, y had to be arriving 10 minutes before x, from 0 to 10 minutes before x. So that's x minus 10. And then what could x be? The minimal value x can be for this to happen is 10. Do you agree? Because that means if x is equal to 10, y is equal to 0. Good. So it's this integral. And then we just now it's just a matter of doing the double integrals. The first integral is x minus 10. It's easy, right? It's x minus 10. And I factored out the 2 over 60 squared. And the next is just integrate this part. And when you solve, you get 25 over 36. Any questions about the setup of the integral? Do you remember double integrals, guys? Yes. Yeah, I agree. There is obviously there is no symmetry. That's why it's theoretical probability. Absolutely right. It's not a realistic problem. So next is Buffon's needle problem. Pretty interesting problem. Let me show you what it is. So you can calculate pi in this following way. You see? So you have you have a ruled paper, and you have this needle. In their case, the needle is half the width of this gap. And what you do is you scatter the needles, and you count the needles that intersect the line, one of the lines. You see, just draw a bunch of them and you have an estimate for pi. Now, why is that? That's Buffon's needle problem. So I think somewhere in the 18th century, somebody made that observation. And here is my statement of it. Maybe I don't remember if it might be slightly different, but obviously. So we have a table, and it's ruled with equidistant parallel lines, and they are a distant d apart. Well, I mean, you're an aristocrat and you have nothing to do, you come up with such things, you know? It's a very interesting question, of course. I mean, who knows how questions arise? There's just you play something, or you have something that comes to your mind. Yes, it was just to help rich people with gambling. That's one of its goals. So again, here we have a table, and it's ruled, and it and the distance between the lines is d. The parallel lines are d distant apart. A needle of length L, where L is less than or equal to d, is randomly thrown on the table. So mine is just general. You see, I have here as distance d, and the needle is just shorter than this distance. Doesn't have to be half, right? What is the probability that the needle will intersect one of the lines? Okay, so how did I think of this problem? So when you drop the needle, I'm going to try to measure several aspects of it. One aspect of it is just through the leftmost tip, I can draw a vertical line, and I can measure where that tip is on the vertical line, right? And another thing is I can also measure the angle. But before I measure the angle, I can see, for instance, if the needle if the needle is leaning downwards, if I look at the left part and it's leaning downwards, I will consider it a symmetric situation of where it's leaning upwards by rotating it around this red line. Does it make sense? So I'm just using symmetry to make my calculations simpler. So anywhere the needle falls, it will fall in this fashion, in some sort of width. And if it's in another width, I can imagine translating it onto this one, and I can always measure the relative y position of the left edge of the needle on the vertical line, and the angle with respect to the vertical line. Does it make sense so far? So if it does make sense, in my setup, what is the range of the this angle, What's the range I have to consider? You see, what's the range? Not 180, no, not the way I set it up. It could have been 180, but you see, I don't want to kind of, you see, so I look at the left part of the needle and I decided to rotate it. So I decided to make it always pi over 2. You see, I mean, it could be 180, but if it points, I want it is easier to set up the problem if I do it my way. You see, I mean, I don't want to consider is it intersecting the bottom line or the top line. So I want to say it always intersects the top line, because the situation where it intersects the bottom line, I can just reflect it and say and translate it to the parameters of the top line. You understand? So if it happens to intersect like this, it's the same as an identical angle intersecting upwards. So that's how I record every information. You understand what I'm saying? I just measure, then I would measure this angle and I say it's the same as if the angle came out here. Yes, Nicholas, you look puzzled. Make sense what I'm saying? So then this is my setup. This is distance d. I have two random variables. One is y, that's the vertical position, and one is the angle theta. And I assume that there is no preference to the angle theta, so it's any value between 0 and pi over 2. And there is no preference for y. It's any value from 0 to d. Yes. So that means that we have a uniform distribution, which is 1 over d, and the other one is 1 over 2 over pi over 2. So it's so altogether my function is 2 divided by pi d, because I'm assuming that that y is independent of theta, right? Where it lands up on the y will not influence the angle. So far, good. So theta is between 0 and pi over 2. So that's where you have 1 over pi over 2, which is 2 theta. And y is between 0 and d, and that's why you have just 1 over d. And since they are independent, I just multiply the distribution, the density function, sorry, for the theta by the density function for the y. And that's what I get. And so now I just wonder, when does it intersect the vertical line? So to intersect the vertical line, it must be the case that what's the relationship between y and theta? Look at it. Y plus the remaining part has to be bigger than d. And what's the remaining part? The remaining part is L multiplied by cosine of theta. So y plus L cosine of theta has to be bigger than or equal to d. Cosine of theta will be this segment, yes? L cosine theta is this segment. So what do I get? I get that this probability is the same as y bigger than or equal to d minus L cosine theta. So that means what? That means, first of all, what could theta do? Clearly, theta could be, L cosine theta is always positive. Well, in the very, very rare exception when theta is pi over 2, it will be 0, right? So L cosine theta is positive. So what I have is y has to be bigger than or equal to d minus L cosine theta. And that means that theta varies from 0 to pi over 2, and y varies from this value all the way to the biggest value it can be, which is d. And here I just factored out 2 pi over d because it's a constant. I can just move it out and I don't have to deal with it until the very end. Yes? So integrating it, what do you get? So integrate this with respect to y, it's just d minus this expression. So it's just the integral now is from 0 to pi over 2 L cosine theta multiplied by 2 pi d. Right, this pi, I'm not sure what this is, right? But you understand. It's just this is the integral. Here I just factored out the density function since it's constant. And what do I get? I get this once I solve this integral. The integral of cosine is sine. Sine at pi over 2 is 1. So it just, this integral is just equal to L. And I get 2L pi d. Yes? And now you can see where that calculation of pi comes from, correct? Where did that calculation of pi comes from? Well, I want to see this probability equal to 1 over pi. Right? Now, how do I make this probability equal to 1 over pi? Well, I need 2L to equal to D, correct? So that means that twice 2 needles must make up the width of my ruled paper. Yes, and if I have its probability as 1 over pi, that means, oh, what I need to do is just if I throw many needles, all I need to do is count how many needles, so it's a ratio, right? So pi is so the number of needles intersecting divided by total needles thrown is equal to 1 over pi. So it means total needles thrown divided by those intersecting the line is pi. Of course, it's a rather inefficient way of calculating pi. You can actually use Newton's binomial formula to figure out pi precisely and efficiently. But you can also use this interesting procedure. Another thing, of course, you can do is if you can draw a disk. Let's say you're a bad shooter. You know, you live in New York. You haven't really learned to shoot a gun, so you shoot randomly into a target, right? And the bullet, you just count how many bullets enter into a disk of radius 1, right? Divided by total bullets in the surrounding box, and you will also calculate pi. That's very nice. Well, you know that, Stephen, yes? One last question. Let x, y, z be independent and uniformly distributed over 0, 1. Compute the probability that x is bigger than yz. Okay, so what does it mean? So if they are all uniform and independent, that means that the density function is the product of the densities for each of the x, y, and z, and each of them are the same. It's equal to 1. So the probability that x is bigger than yz is just what? It's just 0 to 1, 0 to 1, yz to 1. You see, because that means what? Once you specify what is y and z, x has to be bigger than yz. And you have this calculation, and it's 3/4. Can we actually avoid doing integration for this problem? Well, I'm not sure. I have a feeling that it's possible, perhaps, but you see, if it were not multiplication, perhaps much easier. Right? But maybe you still can. It feels like because you see they are identical, so I mean maybe it's equally likely for y to be bigger than xz and all those combinations. Yes. So they're not going to, you don't have this equality. So I think, for instance, x could be bigger than yz, or y could be bigger than the other product or something like that. So you have to be careful. Just but I have a feeling that you can do this question easily. Well, you look like you are falling asleep. So good night, rest. On Wednesday, we talk about the exam. So if you intend to come, please join the session on Wednesday at the same usual time. And if you haven't submitted evaluation, today is the last day. Take care today. Just I think before 12 it will expire. Good night.
Thanks, Professor Arkady.
Yes.
Thank you. Have a good night.
Good night, Shira.
Thank you, Professor. Have a good night. Профессор, между прочим, вы получили мой там этот evaluation? Вы получили? Я там
Evaluation.
Да, я там написал на русском. Немножко было неудобно написать.
I mean, I know. I mean, it's anonymous, so I know that the
Да, да.
evaluation will be.
Не, да, evaluation, да, но та часть, которая на русском, там было написано, можно...
Что, где
Да,
вы
да,
клянетесь, что вы не списывали, да?
Да. Там на русском я написал.
Молодец.
Там легче было на русском.
Окей.
Я всегда считал русский там очень... Просто у меня по теории вероятности не очень-то... логика у меня не очень-то хорошо работает.
Ничего, это постепенно разрабатывается.
Да, и я сейчас, у меня там... Я тоже не хочу там извинения, там всякие, это пол. Надо вкладывать, это точно. Спасибо большое.
There is no need to worry about it in terms of grade. I mean, just whatever is missing, logically or not, it takes a lot of time to just you think about it and it will improve.
Thank you, professor. Только что закончил там экзамен из вектор-анализа. Немножко exhausted. Спокойной ночи. Спокойной ночи.
Yes. All right. So there are actually, Jacob, pretty interesting videos. There is this, maybe equal linguist. There's this Polish guy, and he has those different people. Let's say Polish and people understand Ukrainian, stuff like that. How well do they understand Ukrainian? How well do they understand Slovakian or stuff like that, right? It's actually pretty torturous to listen to a language that's very similar because you kind of semi hear and semi understand and semi not. Right? Yes.
I remember you said that you're Ukrainian. Do you speak Ukrainian in addition to Russian?
No, I mean not at all. I spoke at 4 because I lived in a region where they speak Ukrainian, but I was close to the border, so I barely understand it. I mean, I suppose if they speak slowly and if or you have subtitles, if I can compare to Russian subtitles, it would be very simple to understand. Or if they speak very slowly, I can guess what they are saying. But no, I don't speak Ukrainian.
Because Ukrainian and Polish are the closest I've actually gotten to understanding someone is Ukrainian. Russian I understand, but that's also because a lot of my friends are Russian, so I grew up around that language. But Ukrainian is nearly.
Because it's very. I'm not sure. I wonder if it's closer to Russian or to Polish or just right in between. Hard to say. I mean, I know many Russians. They're very, of course, you know how they are. So to them, it's not even a language. It's a kind of dialect. Right.
Mm-hmm.
So
I know.
Yeah. The word drapezhnik, does it mean anything to you?
Predator.
Okay, so it is Polish or something. It sounds very funny because you see in Russian it's a slang word. Drapать is to run. That's all. But so it sounds like a very funny word, but that's not how we say predator.
Well, it's funny because similar or the same words come up in both languages, but they mean different things. Like drapać, what you just